All right, so I believe we talked about the left half of these all. Yes. On Tuesday. So just for a little bit of additional practice now that we've talked about all of our main rules, I'd like to spend a little bit of time on these 6, 7, and 8 here. So when you're looking at rather long expressions, and the first one of these is maybe of the medium variety of difficulty level from your mastery test. Second one, maybe medium level. The third one here is a little harder. But when you're looking at these, think about the overall structure, or in terms of what rules you're going to have to use aside from individual function rules, the combination rules, the product quotient chain rule. Make sure you see how the pieces are connected to one another. So in number 6, for instance, there's an x squared and a tangent of x. What general structure of pieces, or like how are the pieces of that connected overall? Yeah, that's a product. We've got an x squared and a tangent of x. Tangent on its own isn't anything. It's like square root on its own without anything under it. It's a type of function, but tangent of x all goes together. X squared goes together. Easier to remember. But let's see if I can get this to go or if it's going to. So we've got overall a product here between those two pieces. And if you want to assign names to them, if that's something that's helpful, like call one part f, one part g, or f of x and g of x, since that's our variable here. You can think about how product rule lays out. Number 7 may be more obvious. We've got overall a quotient, or there's lots of stuff going on. There's addition and subtraction as well. But if you're substituting in values for x, the last step would be, and then divide the top by the bottom. You'd have to evaluate the numerator and denominator and then divide. So overall, it's a quotient where we have to think about the derivatives of the numerator and denominator, although just like product rule, it's not just as easy as slapping them back together when you're done taking derivatives. But number 8 does not involve a product. There's a square root of something that isn't x. It's a square root of a whole other function. So it's a composition of a square root function with some other stuff. And that other stuff isn't very simple either. So number 8 in particular is a little tricky. I'll give you a couple minutes to think about these. The first couple might not take very long if you're well practiced at your basic rules. The third one takes everyone a little while. So number 6, this product rule. If you wanted to write it out with thinking of function names to match up with our product rule pattern, product rule is if I have a product of functions f and g, and I want to find the derivative of that, I do need the derivatives of each individual half, f prime of x and g prime of x, but each one gets multiplied by the other's original form. And then the two mix and matched products there are added. So whatever order you want to write the products in, oops, except not derivative again, g prime of x. There we go. So I need f's derivative and f's original, and g's derivative and g's original format from the two halves of the product. By the way, what is the derivative of tangent of x? Yeah, secant squared of x. So don't forget the x part of that. Also known as 1 over cosine squared of x. But the product rule then says that y prime, or dy dx here, would be, I'll just use this order, f prime times g. So 2x times tangent of x plus, the way around, x squared and secant squared of x multiplied together. Questions on that one? Maybe more straightforward. All right, so our quotient here, again, if you want to name the numerator and denominator, you can. You say, like, if you just want to kind of make notations for yourself, if that helps you organize. Other ways I've seen people do this, like the derivative of this numerator, well, the 5's going to go away. 6 is just a coefficient on natural log of x. What's the derivative of natural log of x? 1 over x. So I've got 6 times 1 over x, or all kind of right at the shortcut way, 6 over x. You don't have to do that, but it is pretty short. Derivative of the denominator all on its own would be just 2x, the minus 1 drops off. But again, we don't just get to put those in a fraction, we have to use quotient rule, which is somewhat similar to product rule. It's got this mix and match multiplication. But in this case here, I'll write it this way, dy over dx. The derivative of y with respect to x, or the rate of change of function y with respect to changes in x, would be the derivative of the numerator first, and I'm not going to eliminate compound fractions here. I'm just going to leave this as a fraction and a fraction. Derivative of the numerator times the original denominator, x squared minus 1, minus other way around. So the whole numerator here needs to be multiplied onto 2x. So I'm going to write it the monomial first, longer part second. But the order isn't really important. It's just multiplication as long as it's after the other term. 6 natural log of x plus 5 all over, don't forget the denominator of quotient rule. It's really easy because you're so focused on getting all the numerator pieces in there to just forget to write the denominator. The derivative of a quotient is a quotient, and the denominator is just the original denominator squared. Like this. So I can see that just thinking about other common sense things about math. If you look at the form of this derivative, you can see it'd be undefined if x were either positive or negative 1. So it's the original. So it's good that there's not a derivative value when there isn't a value to the original function, vertical asymptotes and stuff. Also, you can maybe tell that it'll also be undefined if x is 0. And that comes from the natural log function. Natural log of x is undefined at x equals 0. There's a vertical asymptote for that also. It's also undefined when x is negative. So in fact, this derivative, because there's a natural log involved, natural log of x involved in the original function, this function is only defined when x is greater than 0, and it's also not defined at x equals 1 because of that denominator. And those things all carry over into the derivative. The derivative might have additional places where it's undefined, but it shouldn't have values where the original function didn't, because that wouldn't make any sense. So you still have to have a denominator, and it's going to have the same sorts of pieces in it. Even if there were some way to simplify, there would still be the original denominator, at least, left behind. All right, now as for this one, I've got a square root of something, and that something is a sum. It's a sum of two pieces. So if I have to find the derivative of a sum, that's easy. Take the derivative of one piece, the derivative of the other, and add them back together, which, well, half of that's easy, because the 9's derivative would be 0, This part's kind of a mess, though, because it involves chain rule again. So, kind of doing this a piece at a time, if I'm trying to write out the derivative of this, I know outermost function, kind of working from the outside in, I've got a square root function. And the derivative of a square root function is 1 over the 2 times the square root of, well, it depends what was underneath it. But same thing, if it's a square root of x, we get 1 over 2 root x. If it's a square root of something else, we get 1 over 2 times that square root of something else. So all of this stuff here, sine cubed of 6x minus 5 plus 9, is still going to be underneath that radical sign. Or this is just, you could also think of this as power rule. It's all to the lower power now by 1. Instead of a positive half power, it's a negative half power. But not done yet, because we need to multiply by the derivative of, and it's messy to see down here, but it says the same as this. We need to multiply by the derivative of what was underneath, what this was a square root of. And the 9 part's going to go away. But thinking of this, so just as a note, it's sometimes helpful if you're dealing with trig functions, a sine cubed of 6x minus 5. This means the same thing as sine of 6x minus 5, whole thing to the 3rd power. So that plus 9 is what we really need to find the derivative of. And the plus 9 part won't affect the derivative. So we'll focus on what I just wrote here in red. If I need to find the derivative of this, the structure of it right now is, oh, overall that's a cubed function. It's a 3rd power function. It's not a 3rd power of x, it's a 3rd power of a sine function, but that means the derivative is going to be 3 times the 2nd power of a sine function, with some other stuff still. But we've got sine of 6x minus 5 now to the 2nd power instead of the 3rd power, multiplied on in this separate factor. But since it wasn't just x cubed, it was something else cubed, we have to think about what's the derivative of this something else. What's the derivative of sine of 6x minus 5? Well, it's a sine function. It's not just sine of x, it's sine of something else, but the derivative of a sine function is a cosine function. And it's a cosine function with the same argument, 6x minus 5. But since this is not just an x, it has its own rate of change, so we've got one last level of chain rule to deal with. What's the derivative of 6x minus 5? Well, that's just 6. And finally, we're done. There's no more inner part to this. This is a linear function. Its rate of change is 6. Done. So there's a lot of levels to this. This is thinking from the outside in, there's a square root function. It's a square root of a cubed sine function that was of a linear 6x minus 5. So it was 1, 2, 3, 4 levels of chain rule, I guess you'd say there. Function stacked on function in that sense. This is not easy. This would be an example of one of the most challenging sorts of questions on your mastery test. I am going to post, as soon as I get out of here today, I'm going to post an additional, I think it's 45 questions or so, extra medium to difficult level mastery problems for practice so that you can work on those over the weekend. If you have questions, ask in recitation, office hour, something. I'm not going to post the solutions to them. Just ask if you have questions. But you do have a large number of also homework questions in the iMath system where you can try those, see if you get them right, and it'll tell you right away. But if you're stuck on some of these longer ones I post, make sure you come and ask. I will see you again before the mastery test, because it's not till next week, Wednesday night, so 6 days from now. But in any case, let's see. Maybe I have one more thing. But any questions on these before I make this rainbow of derivatives go away? All right. So this one's not quite as messy as the last one. But some aspects are the same. right, so let's do this one maybe the other way around. So starting from the inside, I know there's the square root of some stuff. There's a square root of two terms added together. Added together is easy. Just one of the two terms added is a little bit messy because it's a product. So if I want to find the derivative of what's underneath the square root sign, or the derivative of the pieces that would come first, order of operations wise, I'd need to find the derivative of this product, which tangent we already talked about today. What's the derivative of 7 to the x power? 7 to the x times natural log 7, right? So 7 to the x times the natural log of 7 is the derivative of this first half of the product. And so product rule says we're going to do that times derivative, the original second half, tangent of x. Be careful with dots. I wrote a dot here for multiplication just because there was a 7 and it looked strange. It looks like it was going to be connected onto a 7 tangent x or something. Dots don't do the same thing as parentheses do. So if it was actually a tangent of x plus 1 or something, I'd need to put parentheses around there, not just a dot between. But other half of product rule, the original first half and the derivative of the second half, which we already worked on today, secant squared. Derivative of tangent is secant squared. Tangent of x gives us secant squared of x, and that's the end of the story. So here's the derivative of the squiggle underlined part, which is just connected with addition to sine of x, derivative of which is cosine x. So we've got product rule here plus the second term. This is all the derivative of what's underneath the radical sign. So if we're working from the inside out, this is the rate of change of the first thing that happens, and then I need to multiply that by the rate of change of the second with respect to the first, or the outer with respect to the inner. So all of this, which is 3 lumpy terms here, needs to be multiplied by the derivative of the square root function with respect to what it was the square root of. So that's just the 1 over 2 times the square root of everything as it was, 7 to the x tangent x, plus sine of x. So if it makes more sense to go in the other order, please do. I just wanted to show kind of thinking through chain rule both directions, like starting from the inside working out or starting from the outside working in. You should get the same result either way. We worked out all the derivative of this. The innards here was kind of all one step. It's just a product and a sine function. There's not multiple levels of chain rule here, but all of this is the derivative of the first function, the internal function, and then the derivative of the square root of something is 1 over 2 times the square root of same stuff. So 1 over 2 root x for square root of x, 1 over 2 square root of all of this, since all of this was under the square root sign. All right, let's see. What else do I have? Any more of this? I think that's probably enough for today. Let's talk about something else. So, here we go. So I do want to talk about what's called second derivatives. If I have a rate of change function, yeah. Uh-huh. Okay. Yeah, brackets, parentheses, whatever you, yeah, however you want to write it, that's fine. Yeah, absolutely. All right, so we were talking about just finding derivatives. So when we talked about imagining what this is, it's a rate of change of some function. Now, if you have a function that's already a rate of change function, like maybe you have a formula that tells you the speed at which someone's driving down the highway at any point in time. And from that, we know we can figure out how far you've driven between any 2 points in time. But I could also talk about the rate of change of your speed, because for any function that you have, unless it's a wildly unpleasant function, we can talk about how to measure its rate of change. So regardless of what type of function that is. So if I talk about the rate of change of a rate function with respect to x, the input to that rate function, that's perfectly okay. It's called a second derivative. and derivative of a rate of change. There's no new rules that apply. To find the rate of change of any function, we have a variety of rules that we've already talked about. You can call it a second derivative, the derivative of the derivative, and certain specific meanings of derivatives. There's terminology that goes with it. So what I was just talking about, the rate of change of your speed is called acceleration. But that's just a specific term that comes up a lot, so it got its own name. But that's just the rate of change of a velocity function. It's called an acceleration function. But this second derivative, no new rules, has some new notations just because, well, that looks a little weird. But I can take the changes in my rate of change function with respect to x, some other notations, the prime notation, if it was just called y in the first place, or y prime was the name of my derivative, I could call a second derivative y with two little marks, y double prime, or y prime prime, I suppose you could say. But y double prime, or if I called my derivative f prime of x, I could call the second derivative, or the rate of change of that derivative, f double prime of x, or f prime prime of x. If I had, so dy over dx is a notation that we use for first derivative. I'll specify now. But if I talk about, almost stayed. But dy, I just want to explain why these 2's are in those strange places. So dy over dx, change in y over change in x, or m, our rate of change, that we've talked about forever. If I want to know how fast this is changing, or what's the rate of change of that, didn't mean to scribble there. What's the rate of change of this with respect to x? That'd be saying, okay, well, find the rate of change of this with respect to x. Well, if you look at the notation here, although that isn't really what's going on, you see, okay, d, dy, and then dx, dx. So this notation here is kind of a mutation of what's going on here. No, there's not parentheses around this, because it is just notation. But that's why the 2's are in different spots, because we're not multiplying dy by itself. Just like if I have a function y and I want to find the rate of change of y with respect to x, I can write this, and then simplify it to put the y on the top as if it's a fraction, and then this is y over 1. It's really not, but just notation-wise, this becomes dy over dx for short notation purposes. Finding the derivative with respect to x, or the change with respect to x, of something that's already dy over dx gets this notation. Similarly with f of x, just the f of x is normally not plopped onto the top because that makes it messy. These are all just notations. They don't mean anything different from one another, but if you see stuff that looks like derivative notations but with 2's thrown in, it's talking about a second derivative. If it's got 3's thrown in, that would be the third derivative, or the derivative of the derivative of the derivative. There are very few applications once you get past third derivatives, but there are some, I'm sure. You could find as many as you want with some functions. If you see derivative-looking notation, but it has 2 little marks like this, that indicates second derivative. So just in terms of looking at your notation, make sure you don't skip over little marks and little numbers here and there, because those are important. They're referring to the rate of change, in this case, of a rate of change function. So there we go. So let's think about how a function and its derivative are related. Some of the next assignments, beyond the ones that are just find the derivatives, at practice of finding derivatives, are about looking at pictures of things that are derivatives and trying to imagine the original, like we did earlier, or looking at an accumulation function and trying to picture its derivative, which we did a little bit of that as well. But if I have a function that's increasing, the rate of change, I don't know precisely what it is, but if a function is increasing, then its rate of change should be what sort of number? Positive, right. So if you want to think about changes in y and changes in x separately, if I think about this dy over dx, that is really a ratio. It's not just notation, but we use that as a notation as well. If I think about if I've got a function that's increasing, that means as x increases, y increases, or when dx is positive, dy would be positive. And thinking about that in terms of these, if dx is positive, then dy is positive, makes this fraction come out positive. Similarly, if you wanted to imagine, we normally think about x like increasing, going from left to right, but depending on what the context is, it might make sense to look backward in time or to see what happened earlier in a process. And so if I imagine changing a little bit to the left or making dx negative, if my function was increasing, the increasing word is used indicating time going forward. So if it increases if you go forward, then it must be going down or decreasing as you go backward, which would mean that as x shrinks, y would shrink also. Or this would be a negative over a negative, meaning m is still something positive. So you can think of it either way, but normally we think of dx as small changes in x going forward, just because of just context-wise, it makes more sense more often. But if you have y increasing, your final y and initial y are going to be related this way. So if you want to think of it not just like y is getting bigger, and say, okay, final minus initial would be something positive. And so again, this fraction would just come out to be something that's a positive over a positive or negative over a negative when we have an increasing function, so the rate of change is positive. So if I have a function whose value is decreasing, if y is decreasing in an accumulation function, just exactly the opposite's true, right? The rate of change would be something negative, and we could think about the same things. As x increases, y must be decreasing, or a final y minus initial would come out negative. As we let x get larger, x final minus x initial would always be something positive if you're thinking final minus initial. So we'd get this m value that turns out to be something negative. But we've talked about that concept for a while. If I have an increasing function, it's got a positive rate. If I've got a decreasing function, it's got a negative rate. And that actually applies whether the function we're talking about is something that was just accumulation, like measuring how far I've driven or how much sand is poured onto the scale or how high the rocket's gone, whatever story you want to remember from earlier in the class. If I want to talk about the rate of change of that, I talk about what happens final minus initial to the y values of that accumulation. But I can also use this to relate a rate of change function to its rate of change. It's the same relationships. So positive values of a derivative indicate that the function whose derivative it is increasing. Either way, you can start from knowing a derivative value and know an accumulation type afterward, increasing or decreasing. Or you can start from knowing increasing or decreasing accumulation and then describe the rate of change from that. But it's any function. Notice it says values of the function are increasing and decreasing. It doesn't have to be any specific type of function. Any function that I start with, its derivative is going to be positive if that function, the original function, was increasing. It's going to have a negative derivative value if that function is decreasing. And so that works for something that I call f and its derivative f prime. It would also work for something that I was calling f prime in the first place and talking about its derivative, which would be called f double prime. Meaning, thinking about the values on the right pertaining to something that's already a rate function. If I say that the rate at which something's changing is increasing, so maybe the rate at which the rocket is rising into the air is increasing. It was going upward at 2 meters per second, then it was 3 meters per second, then 5 meters per second. That would mean that the derivative of that rate function, the second derivative, or acceleration, since that one has a name, would be something positive. If I had a rate of change that was something decreasing, so maybe the population of a certain town was decreasing by an average of 100 per year, then by 50 per year, and then decreasing by 20 per year. So I can have a rate that's decreasing like that, and I can talk about then its rate of change is negative. So those decreasing value, and it gets a little bit confusing sometimes talking about, wait, what is decreasing? Is the rate decreasing or the rate of change of the rate decreasing? So it's important to try to maybe visualize graphically what we're talking about. So let me just, a couple of visuals that maybe go along with this. If I have a function that's increasing so that its derivative is positive, you can see here, where f double prime, the second derivative of something, is positive, this would indicate that the first derivative increases. So thinking about if the first derivative is increasing, that makes the second derivative positive. Just think this first fact here, but thinking about values of the function, thinking of the function as a derivative, as a rate function. So if I have a rate function that's increasing, the values of its derivative, the second derivative overall, would have to be positive. So if I think about what that means about what the original going back to accumulation, if I have derivatives that are increasing, whether it was something that was 0 derivative becoming a derivative of like 1, a derivative of 2, a derivative of 3, or something negative that's becoming less negative, a derivative of -5 that's suddenly becoming a derivative of -3, -2, -1, 0. If I try to imagine what that would look like in terms of the accumulation function, so the left half of this, let me scoot this guy out of the way, maybe. There we go. So if I have an original function of this form, this kind of curvature, which is called concave up, like an upward-facing parabola, but it doesn't have to be a parabola. But if I think about the derivative values of something that looks like this, call this f, and I think about the values of f prime would be something negative here. I'm just going to pick a negative, like -3. And as I go to the right, the derivative is still negative, but less so, maybe like -2, -1, a derivative of, well, it seems almost horizontal here, so locally this seems to be about constant values of accumulation, so about 0 rate of change. But I can see that I've got this function increasing, so it must have positive derivatives over here, although they start out with low positive numbers and become higher and higher. So from left to right across this whole shape, I've got derivative values that start negative, become less negative towards 0, and then continue increasing into the positive. So throughout this graph, I've got a sequence of increasing derivative values from negatives to zeros to positives. But any section of this, I can say that I have a second derivative that's positive, whether I'm just talking about over here, over there, or the whole thing, because throughout, since the first derivative, the rate of change of what we see, since the first derivative is increasing throughout from negatives to zeros to positives, that means that the second derivative has to be positive. Positive derivative indicates increase. So the derivative of the first derivative must be positive for something that's shaped like this. Similarly, if I think about negatives, if I have any function that's decreasing, then its derivative must be negative. So that includes if I have a first derivative of something that's decreasing all the time. So first derivative decreasing would be kind of the opposite of what we were talking about before. A derivative or rate of change starting at larger values and getting smaller and smaller. So maybe starting at positive values, getting closer and closer to 0, and then into negative. So this would be decreasing steepnesses the whole way, if you want to think about slope or steepness, or decreasing derivative values all the way along from left to right. So the derivative of this graph is getting lower all the time. It starts at a positive number, turns closer to 0, gets to 0, into the negatives, and so forth. So since the derivative value decreases from left to right along this function f, that's f prime is decreasing. That tells us then that f double prime, the rate of change of f prime must be negative. The first derivative is decreasing all the time, so its rate of change is negative. And the rate of change of a derivative is a second derivative. So just in terms of describing shapes of graphs or knowing values of derivatives, they can tell you visually kind of whether an accumulation graph is going up or down, but you can do the same with derivatives. You can picture whether derivatives, if you're trying to sketch a derivative graph, you can do that. If you're trying to sketch an accumulation graph, we can do that. Just based on positives and negatives and zeros, those are kind of helpful, can help us put all of the pieces together. So there we go, oops. What we're going to use this for is something called optimization. So optimization involves finding the best value in a situation, and usually best is like least expensive, highest, least amount of material, most profit, things that are maximum or minimum value of some quantity. And how we can find these locations has to do with patterns in the derivative. So although in algebra it's easy to solve for when does the output equal a certain value. Not always easy, sometimes it involves ugly formulas or factoring of awful types. But solve for when does this output equal 0, or when does this output equal 1 million, whatever you need to find. But when does the output reach a maximum? There's not like a set equal to maximum and solve for x. That's not a thing that you can do just with algebra, but using rates of change and analysis of those, we can figure out when our rates of change tell us that we're at a maximum or a minimum, if that's what we're looking for, optimum in general. So a critical value is the name of these magic spots where maximums or minimums could occur. What we're going to do is try to narrow down by looking at properties of the derivative or properties of the rate of change where these key spots are going to be. So a critical value is a spot on a function, an x value or input value, where we have an output, key, you have to have an output there, and one of two things happens. You need to have a derivative equal to 0, or a derivative that doesn't exist. And this seems like, well, that's a weird list of things. But if you can imagine trying to find, oops, sorry about that. If you can imagine trying to find like, I know this is going to go away anyway, so. Some graph or another. Like, all right, so where does this reach its maximum? Well, at a spot like that, it would reach its maximum. The derivative is positive to the left of a maximum, negative to the right of a maximum, because you'd have going uphill and then going downhill. Like, oh, that means I must have been at the top of something. And right at the top, if it's smooth, like this was when I drew it, then we can say in a small neighborhood right around this key spot here, let me just call it A, at x equal to a, the derivative or the rate of change of this function is about 0. Because it seems to be relatively flat. If I move a little bit to the left or a little bit to the right, I might get something slightly positive or slightly negative. If I pick just the right interval right around there, I might get exactly 0. But this rate of change, if it's a smooth top to a hill, not a weird jagged mountain sort of thing, would be 0. Or notation-wise, if this is called function f, since f was used up there, f prime at a would be 0 at that spot if this is a smooth top to a hill. If I'm looking for a maximum, if I could find all the places where the derivative is 0, setting equations equal to 0 and solving is something that we can do, then I can locate that position there. So it's just that there's other sorts of spots also where maybe it's a not quite as nice function, something like this, where there's clearly a maximum going on here, I'll call this function g, but g prime at this a, it's not, I can think about g prime to the left was positive. It was increasing up until I got to a, and then decreasing after, but right at a, it's not that the function isn't defined, but just that the derivative, if that's a sharp corner, like a cusp is the name of this, like a curved vertex, there's not a derivative value there, because if you try to zoom in to find a constant rate of change due to the abrupt, it was going up and then it stopped going up, it was just going the other direction suddenly, there's not a derivative. So this g prime at a doesn't exist. And so either of those would be spots that would be called a maximum of a function. So these, the way I drew them, they're the maximum, as in there's nothing higher anywhere else. Sometimes we're just looking locally to find, so what's the highest around this neighborhood, because this is the only domain that makes sense in context. But those sorts of points, whether I'm looking at an entire domain of a function or just a subset of that, if I can locate all of these key points, these critical values that make the derivative 0 or undefined, that's the only sorts of spots that could be maximums or minimums. Because I could flip both these graphs upside down. We could say the same thing about minimums. It could be a minimum because it's at a sharp point, or a minimum bottom of a hill. The derivatives at those two spots as minimums would also be 0 or undefined. So we can't tell which it is just from the derivative value, but just that there's something of interest going on there. So there's a few other options for what could happen. But thinking about just these maximums, if I think about the pattern of the functions, functions in both of these cases were increasing and then decreasing with something else in between. In the case of the smooth curve, it was increasing, then went to this momentarily constant 0 derivative. If I zoomed in right at the top of that hill without the star drawn on top of it, it looked like a horizontal line or a constant rate of change approximately 0. No such luck on this bottom one. If I zoomed in closer and closer, I'd just see, oh, it's still a peak there with negatives to the left and positives to the left and negatives to the right. But either one of these shows me I've got a maximum because I've got increasing function to the left of this critical value and then a decreasing function to the right, where the function is actually defined all along. There's not a vertical asymptote here, it's just a weird pointy spot. Lots of radical expressions with nonlinear expressions underneath end up looking like this. Like if I do a third root of an x squared or something, those sorts of things tend to have weird cusps in the middle. So let's see, clear this off for a moment. So critical value are those sorts of values that correspond to those two types of places so far. There's a couple other sorts of places they could correspond to. There we go. But if I have a derivative that's equal to 0 at a specific spot, they used C, I used A, then that means that the function, it doesn't really stop. It's not like time stops. But if you zoom in really closely, the increasing and decreasing, whatever was going on, it stops doing that momentarily. And then you have to see what happens on the other side in order to know what's going on. But if I have a derivative equal to 0, the button here, then I know that I'm pausing away from increasing or decreasing, at least for a moment. So we could have that first situation I drew. We could have that maximum. Nice smooth, goes up, hits a flat top to a curve of some sort, and then goes back down, like this. So if I imagine function f as I go from left to right here, let me move this guy out of the way. As x increases, y increases, and then pauses and goes back down. It doesn't really pause for too long, but you can see the arrow at the bottom, or the x value is increasing at the same speed all the time. But you can see the vertical arrow moving up and down. It looks like it kind of stops at the top for a moment. It's not that it's actually stopping, it's just that it's hardly moving up at all and then hardly moving down at all. So for a little bit, it looks like it's kind of stuck. But that's really just the corresponding changes in y matched up with the changes in x. So I could have a maximum, local maximum, because I don't know what else is going on. I don't know that there's, it could be a polynomial that goes up and down a bunch of times. But if I have a derivative equal to 0, I could have something like this, where I increase and then pause and then decrease, which would mean that my rate function, let's see, the rate of change of a function that's increasing is positive. If this pauses for a moment, I can say, well, it's not really a whole interval there, but for a moment, I can imagine that the rate of change is 0. And then when f is decreasing, its rate of change would be something negative. So if I have a function that's increasing, then kind of turns around and starts decreasing, then I know the derivative would be positive, hit 0, and become negative. Or I could even sketch the derivative. It'd be something decreasing all along. Maybe it looks like just kind of going downhill. But I know it has to be going downhill from positive values, hit 0, and then become negative. So what about the rate of change of that rate function? If f prime is decreasing all the way along from positive to 0 to negative, what do we know about f double prime, the rate of change of the red f prime here? Yeah. If f prime is always decreasing, then its rate of change is always negative. So just kind of matching these concepts together. So in terms of if I have this kind of top of a hill, more formally local max or local maximum at x equals c, then I know some facts about the types of values or the pattern of values for f prime. I know that they were positive, then 0, then negative, which is a decreasing sequence of number types. And since that sequence of number types is all decreasing, regardless of precisely what values they are, then the rate of change of this rate function is always negative. So if I were graphing it, maybe it'd be something down here. Maybe a horizontal line, maybe not. Depends on exactly what shape this f is. Whether this is a straight, if this was a straight line going downhill with a constant slope that's negative, then its rate function would be a constant with a negative y value throughout. But we don't have enough details to do that sort of analysis here, just general shapes. So what if I had a local minimum instead of a local maximum, so the flipped upside down? Think about the same analysis we did above. Think about what sort of pattern the y values have in this original f function. What's the pattern of the y values in the rate of change, f prime function? And what sort of values would the second derivative, f double prime, have? All right, so just thinking about f, as I go from left to right, my y values, it's not this pattern, but from left to right, I've got y values that decrease, kind of pause for a moment almost, and then increase. Decrease, pause, increase. So if I'm thinking about the rate of change values, not specific numbers, but just what type of numbers they are, if I've got a function that's decreasing, its rate of change would be negative. And then it smoothly goes through this pause and then increase. So that's negative to 0 to positive values of the first derivative. So maybe, maybe it's some sort of line that goes up like this, or just something that goes from negative, hits that spot on the axis, and goes up somehow or another. But if this function is going from negative to 0 to positive, that means that however it might be doing so, straight line or otherwise, this rate function is increasing all the time. Meaning its derivative, the second derivative of f, the purplish function, is always positive. So you can imagine, like, okay, if this is going uphill in an exactly straight line through that, then that would be one constant positive rate of change, and I could graph this as a horizontal 1y value second derivative, but I don't really know other than just it's going uphill somehow or another, so this would have all positive values somehow or another. All right, so there are a couple of other possibilities what could happen here. These are the ones we'd be looking to find. If you're trying to find an optimum value, and the process for doing this takes a while, but if you're trying to find an optimum value, you're looking for one of these things. If you're trying to find a maximum, you're hoping to find a pattern of increase, pause, decrease. So a 0 of the derivative, where your function increased and then decreased afterward. Or if you're looking for a minimum, you're looking for the reverse pattern of increase versus decrease, but derivative of 0. Or even if it's undefined, that's okay. As long as it's that decrease changes to increase and the function stayed defined, although it could have been pointy, that would be a minimum. Those are things you'd be looking for potentially. However, if you don't know what you've got and you're just trying to find x values, you could end up with something that isn't what you wanted. You're not necessarily guaranteed that you're at a maximum or a minimum, because we have to have a change from increase to decrease or vice versa. And there are plenty of functions that don't do that. This shape, for instance, something like an x cubed graph. They have this, it was going up and then it flattens out and then it continues going up. So that flat spot is kind of like a plateau, like a resting spot, but it didn't change direction. The derivative didn't change signs. It just hit 0 and then continued on the way it was going in the first place. So this function f, you can see, is just increasing most of the way. It just happens to pause for a moment around C. So increase and then this pause or this flat spot, and then increase again. Which, if you had a graph, you would know that that wasn't a maximum or a minimum. But if you're just looking at patterns of values, and you saw, oh, I've got a function that's increasing, hits a derivative of 0, and then increases again. Or if I had information about the derivative, it would be this sort of information. The derivative 0 at this critical value, but it's positive on both sides of it, meaning, oh, it didn't change direction. My original function didn't change direction. It just was actually a pause or a flat spot in the graph. But if this function, this rate function, regardless of that, has a 0 derivative and is positive on either side, I can maybe imagine, oh, if I were trying to sketch this function, it would have to have positive values, hit 0, and then have more positive values, which looks kind of like the original graph we had before. So its derivative would be, well, since this left side would be decreasing, and then the right side would be increasing, if I have positive values that hit 0 and then become positive again, f prime's derivative would have to be first negative, and then 0, and then positive. So although this flat spot here isn't a minimum or a maximum of function f, it is actually a minimum of function f prime. It's not a minimum of this function or a maximum, it's just this flat spot. But you can see in the visual, thinking about the steepness in that, that's definitely the flattest spot in the whole graph. That's the minimum value of the derivative. There's no negative values of the derivative in this curved graph. I can tell that because it's always going uphill or flat. Flat is the least the derivative hits, and that's 0. So this is the minimum value of the derivative at that spot. Similarly, we could have something going the other direction, kind of going down a hill and stopping at a little plateau. So I have a negative derivative for a while, or my function's decreasing until it hits a flat spot, but then continues decreasing. Meaning I've got a negative derivative, and then 0, and then it's more negative again. So although it does have this pause or a spot that you could solve for where the derivative is 0, it doesn't necessarily mean that I've got a maximum or a minimum. It just means I've got a place where the y values kind of hover for a moment. And in this case, it's hovering between going down and going down again, as opposed to going up then down or down then up. So the rate of change of this second purple graph here would be negative almost the whole time, just hitting 0 for a moment in the middle. Which would mean if I were trying to sketch this f prime function, it would have almost all negative y values. Just hit the x-axis right at c, and then go back down somehow or another. So in order to do that, to be negative and turn to 0 means that it's increasing, and then going from 0 back into the negatives means that this rate function is decreasing. So reverse sort of pattern as the one above, but increase, pause, decrease. The y values in this mean that its derivative is first positive, and then 0, and then negative. So this spot here in the second graph is actually the maximum value of the derivative. The derivative, f prime, although we don't have a sketch of it, was increasing, then pause, then decrease. Increase, pause, decrease. That's a maximum right in the middle. And although it's like, oh, well, that doesn't look like a maximum, that's flat. Well, all the rest of the values are negative, so 0 is a maximum compared to all the rest of the values here. So just keep in mind, negatives are less than positives. It's very easy to just start thinking about, oh, what's the steepest going either direction to find a maximum of a derivative. Maximum would be like largest positive numbers, next would be 0, and least would be the negative numbers. But in any case, the first derivative equal to 0 happens at a variety of spots in all sorts of functions, but it's not always a maximum or a minimum. If you can find it, however, those are the only possible locations of maximums or minimums, other than, in specific contexts, endpoints that are artificially created by saying, oh, well, we have to stop at 0 because it doesn't make sense. Otherwise, that could be a maximum at 0. Doubt it, maybe a minimum. But in any case, I'll stop at that for today. I just wanted to kind of introduce some thinking about derivatives and second derivatives and their interrelation to one another. Yeah. I'm sorry, what was that? Oh, so if I were trying to sketch this, it would have to have positive values, then 0, and then negative values. So this center graph would be going up and then down. This would be just going down through that C spot on the axis. All right, so study. I'll post some additional mastery questions, but I'll also post some new homework that relates to this stuff if you want to take a break from just memorizing things.